Welcome to the Certified Local Government Virtual Summer of 2021 series offered by the North Carolina State Historic Preservation Office. My name is Christy Brantley and I'm the Local Government Coordinator. If you have any questions or would like additional information regarding today's session, please feel free to email me. A screen with contact information will be shown at the conclusion of this video. The third series of our 2021 training series will be presented by Restoration Specialist Brett Sturm. Brett joined the HPO staff in 2017 as a restoration specialist for an 18-county area in the central Piedmont. He holds a bachelor's degree in history from the University of North Carolina at Chapel Hill and a Master of Science in Historic Preservation from the University of Pennsylvania, where his primary focus was the conservation of brick and terracotta. Prior to his tenure within the HPO, Brett worked as a project manager for a general contracting company specializing in historic home renovations in Center City, Philadelphia. Brett is thankful to help advance preservation work in a region of the state encompassing his own native county of Mecklenburg. As a restoration specialist, he provides technical assistance to local governments, private building owners, and nonprofit organizations on old building quandaries of all kinds. He also consults on and reviews building rehabilitation projects seeking federal and state tax credits. Away from architecture and history, Brett's primary passions are ceramic arts, gardening, guitar playing, and rowing. Welcome, Brett. Thanks again for agreeing to present, and we are looking forward to hearing from you.
So this is my second opportunity to record a CLG training at home session for the YouTube channel. It's an exciting thing to do. It's a great way to reach people all around the state when we can't travel as often as we would like. This particular topic, sustainability in historic buildings, is a very interesting one. It's a very important topic. This is actually the first presentation I've put together on this topic. And I'm looking forward to doing it in the future and refining it. And so I would say that if any of you watching have comments or additional questions or suggestions for more content in this area, please let us know. Because sustainability is a thought on all of our minds these days, if you follow the news or if you experience the weather. And when I was putting together this talk, I very intentionally didn't want to include any scary images of wildfires or hurricanes, because I know what's on everybody's mind, and we don't really need to see images of that all the time when we see it so much in the news. So we know the challenges that we're faced as the climate continues to change here on planet Earth, and we know the future is uncertain. Recently, the Intergovernmental Panel on Climate Change released its sixth assessment report, which was the biggest sort of conglomeration of scientific data on the climate to date, which concluded that worrisome levels of warming are going to occur this century, and at a rate that's quicker than I think anyone has expected, unless we experience achieve deep reductions in CO2 emissions. And so this is the reality that we face here, and it affects how we live, and it affects the buildings in which we live. I'm sure if you're viewing this from the North Carolina coast, perhaps you've already seen buildings around you being elevated to be more resilient in the case of flooding or sea level rise. If you live in any of our larger cities, like here in Charlotte, well, I should mention that previous image was from New Bern. If you live in any of our larger cities like Charlotte, you've probably seen infill construction occurring in older neighborhoods, and these buildings at least project an image of modernity and efficiency. And that's probably weighing on your mind as you contemplate your own historic home. If you have a mailing address anywhere in the state, you've likely received marketing materials about thermal efficiency in buildings that put before you various messages telling you that your concerns about the performance of your house warrant dramatic action. And so You might be thinking, as a historic homeowner or as someone who sits and volunteers his or her time on a local historic commission, what should I do about this? How can I contribute to becoming more efficient and more environmentally friendly? I've got to do something. My house is inefficient. I need to do something. I need to act. And also, my energy bills are high in the summer and high in the winter. So you can rest assured there is a big industry that is ready to monetize your concerns over building performance and efficiency. This is the green building movement, and it is not a bad thing. I don't at all mean to disparage the green building movement or the impulse to be more efficient with architecture. But in the case of historic architecture, we have to ask some critical questions here. Do materials manufacturers know our house and know what's best for our house? What are their motives, in fact? Contractors that market efficiency upgrades, do they have your best interests at heart? Are they thinking about the long-term well-being of your house? And are you as a homeowner equipped with the knowledge you need to make good decisions in this arena? Do you know traditional materials, how they behave and perform, how they respond to different treatments? Do you understand traditional design and construction? Do you understand the physics of how buildings perform in changing climatic conditions? Now, don't worry. We're here to help. We're here to help you make those decisions that will improve the efficiency of your home without compromising its well-being or historic integrity, as sometimes, unfortunately, we do see. In this case here, this is what I would call a spray foam disaster on a wood frame building, early 20th century here in Raleigh. So the point of this talk is to take a look at old houses through the lens of sustainability. And broadly speaking, we're going to do 4 different things. First, we're going to talk about appropriate expectations for building performance in a historic context, and we're going to examine some of the common misconceptions about how old buildings perform. We're going to take a closer look at the physics, the physical dynamics that determine old house performance. I'll try not to put you to sleep. We'll then talk about some specific green building practices that do and don't jive in the old house context, why they do and why they don't jive. We'll discuss that. And finally, we'll end with some tips on what can be done to your old house to make it more efficient in a preservation positive way. So, analogy. I like analogies. Here's an automotive analogy. We see in front of us 2 different cars. We wouldn't argue that these are not cars. They have 4 wheels. You could get in them and drive them, take you from one place to the other. But is any of us going to argue that Ford Model T is really the same animal as a Tesla Model S? Obviously not. And in fact, is there any measure of reconstructive work that you could do to a Ford Model T to make it as efficient and technologically advanced as a Tesla Model S? I don't think you could. I think you can take apart a Model T and down to the nuts and bolts, and you really would have a hard time putting it back together as a Tesla. We can apply this same thinking without judgment to architecture. I call this setting realistic expectations. When you buy or live in a historic home, you have to understand that without extensive reconstruction, most historic houses in our part of the country, by virtue of their construction, how they're put together, are simply never going to perform like a high efficiency house on the right is a passive house, a net zero energy consuming house. It's just simply the truth. In my background, I've actually had the privilege to sort of work in both areas. When I was in Philadelphia working as a contractor, my company actually was hired to do a passive house, 2 passive house standards from Germany, which involved, blower door tests and trying to make the building envelope as airtight as possible. And I saw how difficult that was to do, even with the most modern materials, starting from scratch. And then having the experience to work on old buildings, taking them apart, putting them back together, you realize that they're fundamentally two different animals. And so adjusting those expectations is really important, to making good decisions and making good decisions in the face of so much marketing and social pressure surrounding green building. So we start with that. And furthermore, is a chrome bumper inferior necessarily to a plastic one? We have in historic buildings materials of value, design of value, and quite a bit of beauty, not to mention historical significance and meaning. So, and these two pictures illustrate what I consider to be some non-renewable resources that you find in old buildings, like old growth pine, for example, on the left, and hand pressed brick, early 19th century brick on the right. So there is inherent value to these structures, even if they're not super state of the art in terms of their performance. We need to remember, however, that houses have always, people have always wanted to be comfortable in wherever they take shelter. So old houses were designed for comfort. This was just before comfort is as comfortable as it is now. And a catchphrase or a bit of jargon that I like to use to describe the wisdom in old buildings and how they were put together is vernacular design, which describes a type of building that's based on local needs, materials, and traditions. And sort of like things in the natural world, like flowers, architecture has evolved over time to suit patterns in the local environment, including weather and climate. I'm not suggesting that we dump our air conditioning and go back to the Stone Age, but I am suggesting that understanding vernacular techniques for how buildings originally functioned without mechanical ventilation, without air conditioning, understanding this and also understanding the physics that are at play, some of the science of how buildings heat up, how they cool down, how they get wet, how they dry out. Understanding this will not only help you appreciate the inherent value of your house, but it will help you augment it, make it perform better in ways that don't lead to physical trouble, to problems. We don't want problems in an old building. So step one here is to talk a little bit more about vernacular design and some of what I would call the inherent wisdom, the inherent efficiencies that were designed into buildings before the age of air conditioning. We got a couple concepts to review here. First is what we would call passive ventilation, non-mechanical ventilation. So one of the takeaways from this presentation, if you hear anything, hear this. Old houses have inherently and irrevocably porous building envelopes. When we say building envelopes, we're talking about the borderline essentially between interior and exterior in a house. So that it's the roof, the exterior walls, foundation. If it's an open crawl space, we might be talking about the subfloor level here. Building envelopes is where the outdoors meet the indoors. And you'll hear a lot about building envelopes when you're in the green building world and the modern construction world. You might even know that in contemporary construction, usually the goal is to have a tightly sealed, air-sealed building envelope. Old houses, that you're never going to achieve a tight building envelope, period. And contractors will tell you that it's possible through different means and different alterations. It's never going to happen. Old buildings were meant to breathe. We're going to talk a little bit more about that cliche that old buildings need to breathe. But stopping air infiltration in an old building is essentially impossible. And it's not a mistake. So specific architectural features have evolved to allow for natural airflow through a building because air movement creates a cooling sensation when it's hot. And I will say that we're going to be speaking, we live in the Southeast in a fairly hot, humid climate. So we're going to be talking more in this presentation about the summer months than we are going to talk about the heating months. And I realize it's expensive to heat a house, and we will refer to efficiencies that can be gained in the heating side as well. But in North Carolina, practically, we have a much longer cooling season than we do have a heating season, and the way the climate's going, that trend is likely to continue. So, back to these features, the vernacular features that evolved to promote airflow. We have open crawl spaces, right? Chickens used to run through here too and grab your termites and your carpenter ants, and it was a nice little symbiosis. But air was always moving underneath the building traditionally. And you will see here in the 1950s, with the advent of air conditioning, a lot of open crawl spaces were filled in and enclosed on historic buildings. And we're going to talk about why that's not always ideal and how that's caused problems for buildings. But operable windows, transoms, allowing air into corridors and through sort of the interior passageways of a building. And attics, we see in this attic, this is an 1830s building, we have windows, operable windows inside the attic. We have random roof sheathing. Now you do see that someone's gone on top of that with plywood, but originally this is plank roof sheathing with big old gaps in between to perform basically like a sieve. Air would come up through here and meet the underside of a shake roof, maybe later a metal roof, but always airflow, always air flowing through the attic. That's not a mistake. Okay. High ceilings, chimney stacks, cupolas, staircases, all these features that have evolved to promote airflow. And we'll talk about how air moves naturally through a building from a sort of physics level here momentarily. Siding on studs, something that we see in houses built mostly before the 1920s. This is my colleague John Wood leading a group of students on some repairs from the UNCG preservation program. So before the advent of air conditioning, passive ventilation in buildings and air infiltration was an asset. And the picture now is a little bit more complicated, and we're going to talk about that later. But that's vernacular concept number one, is passive ventilation. Number two, management of solar gain, sun exposure, and then warming from the sun. And so oftentimes when we'll go into the field and we'll see an old house, an old farmhouse, where the builders had an opportunity to sort of pick how to orient the house on the land. You'll see that the long axis is oriented east-west, so that the broad side of the house is facing neither direct morning east sun or really hot late afternoon west sun. That's just a trend that you seem to notice. Porches are often built along the south elevation, and if possible, they'll extend along an east elevation. This is one of the best porches I've seen in my four years on this job. This is a house in Montgomery County. A couple houses that have been joined together over time. And then what we call deep eaves. Deep eaves like these with exposed rafter tails is not just a fashion statement. They look cool and they help us sort of date a building. They're characteristic not only of Victorian buildings like this one, but of bungalows and craftsman style buildings. But not just a fashion statement, because check out the long shadow that this eave casts on the exterior wall of this building. Eaves help break sun exposure, keep a building cool. So that's another brief concept to look into. And then a final vernacular concept is the value of thermal mass, of materials that are either are not great conductors of heat, like wood, or materials that when assembled in a really thick, heavy assembly, wall section, for example, take a long time to heat up and a long time to cool down. So of course, not all houses were as grand as the Hezekiah Alexander house here in Mecklenburg in Charlotte, so oldest building in Mecklenburg County. By no means, this is an exceptional house for its time. But even more common, log houses. Think of log houses. Wood is a poor conductor. And historically speaking, most roofs in North Carolina would have been split wood shake, thick wood clapboard siding. So, and then some vernacular ideas were imported directly from overseas, like the fabulous Single Brothers house in Old Salem in Forsyth County. This brick infill we call nogging. And I don't get to see a lot of this in my service district. I don't have Forsyth County, but if you're in Forsyth County where the Moravians had imported their building knowledge from Central Europe, you see a lot of brick nogging that will even survive behind siding, later siding. And so, brick, there's a lot of air entrained in brick. It's a good insulating material. So brick nogging is a vernacular insulation technique, building thermal mass in a wall section to help keep it cool. And not to mention a ceramic tile roof, very heavy, thick thermal mass, good insulating material. So back to the thinker slide here. Step one was to talk about some of these vernacular aspects of building efficiency, but now we're going to talk about the principles, the physics that govern how buildings perform. And these are sort of two tools to help you make good decisions on a historic house. Lesson number one, psychrometrics. I wonder how many of you have heard this term before. I had never heard it before I went to grad school to study old buildings, and I have to admit it was a challenging one. And I'm not going to say the term psychrometrics more than that'll be the last time I say it as part of this presentation, because we're gonna get a little bit more simple with it. We don't need to go too deep into this, but it's enough to know that it's the study of air, atmospheric air. And air, what is air? It's a blend. It's a blend of different types of gas and water vapor. And air is subjected to both energy, thermal energy, and pressure, atmospheric pressure. And all these things are changing at all different times. And so when you get into psychrometrics, you'll be exposed to these perplexing curves, which they show you the relationship between humidity and what's called dry bulb temperature. We're not going to get that far. It's too confusing. Even MacGyver doesn't understand it. We're going to take psychrometrics and simplify it to what I call the sweaty glass principle. And this is a site that's familiar, I think, to most North Carolinians, right? A nice glass of sweet tea with some ice in it outside in the summer. Glass sweats, right? Do we understand why it sweats? Well, let's talk about something called dew point. Dew point is a temperature, and it is a special temperature. It's the temperature at which a volume of air will achieve humidity of 100%, saturation point. And at this point, the air can't hold any more water vapor, water in its gaseous form. If the air starts to fall below dew point, that water vapor is going to come out of the atmosphere in its liquid state. And in weather, we recognize this as fog or rain. We see it in the morning on the grass as dew, or maybe even on the sides of our buildings in the morning. And in architecture, it's condensation. So dew is condensation, of course. But condensation is what we're concerned with when we're talking about old buildings. So in an old house where, like I said, air infiltration is an absolute certainty, when you have air conditioning inside of that house, you're going to have surfaces that get cooled down by the air conditioning. And the temperature of those surfaces may actually cool to or below the dew point temperature of the air that's coming in, that's infiltrating. And that can be a problem. It's not necessarily a problem, but it's a reality, okay? And understanding the sweaty glass principle, when we're looking at buildings from all different angles, when we're thinking about problems that you can see or problems that might occur, remembering this principle and understanding the basics of how it works is going to help us anticipate, prepare, and control prepare for and control the potential for condensation in buildings, okay? So always keep that sweaty glass in your mind. And if you still don't quite understand why a glass sweats outdoors in the summer, slow down, take it in pieces, and try to grasp that. And because it's going to help us inside an old building. The stack effect. You saw this image earlier in the presentation, and we are taught in elementary school the old maxim that heat rises. Right? We all know that heat rises, but have we thought about why and what that means? Well, the stack effect is really what it means, is what it is. And I would describe the stack effect this way. So as a volume of air warms up, the molecules in the air get excited and they start bumping around, moving, hitting each other, moving farther apart if they can, which makes the volume of air less dense and more buoyant. And just like a balloon, then it's going to want to rise up, okay? As warm air rises within an enclosed space like a building, pressure will build, atmospheric pressure will build. And that air will seek to escape that space, and it will, if it has a route like a louver vent or an attic vent or in between roof sheathing, through siding, it's going to escape. That leaves a void. It leaves a void in the lower parts of the house, down low. Negative, that's going to result then in a negative pressure zone, which cool, denser air is going to try to fill. And so when we feel drafts in houses, that's what's happening. Here's a good graphic that illustrates that. So you have warm, moist air rising within a column, and it's going to be replaced by infiltrating cooler air into the negative pressure zone that it leaves behind. Also worth mentioning, and this is always for me sort of counterintuitive, we think that humid air would probably be hotter, right? Because in the summer when it's hot outside and humid outside, we feel like it's a heavy atmosphere, right? It's harder to breathe, harder to walk around. Well, actually, water vapor is lighter than oxygen and nitrogen. And so humid air tends to rise as well. So, and we observe this in buildings. I have the next slide. You're going to see a couple images that illustrate that. But understanding stack effect, as well as dew point, it helps us anticipate how air is going to flow through a building. And with the flow of air, we know how heat is moving, how lack of heat or cold is moving. We can better understand how humidity and moisture is moving within old buildings. So stack effect is a really important physics concept to have in mind, okay? So we got sweaty glass principle and stack effect. Stack effect in action. Think of the biggest chimney you can imagine in North Carolina. The Cape Hatteras Lighthouse is a giant chimney, essentially, one big enclosed volume of air. Well, inside of the Cape Hatteras Lighthouse, we are finding that, generally speaking, problems caused by moisture, like here, the corrosion of the beautiful metal staircase, or perhaps some flaking of paint, that is tending to occur the higher up you go inside of the lighthouse. So just like that graphic on the previous page, look, it's one big column of air. This is where we would expect the moist air and therefore the humidity and the condensation potential to go higher up into the lighthouse. You can sometimes see this if you go into an old house that's been shut up for a while and closed, and there hasn't been much chance for air to escape the house. If you go into a stairwell, and this is an 1830s house in North Mecklenburg County, sometimes you'll see mildew that is accumulated higher up, the top level of the staircase, at the top of a tall ceiling. That's because that's where the hot, humid air is building up and dwelling. So stack effect is real, and it's going to determine how we treat, how we try to make buildings more efficient, okay? Finally, sort of tying this all together, a third really important physics concept is to understand how materials respond to moisture right? So we know about condensation, we know about airflow. Now we're going to talk about moisture and materials. And we need to understand that a lot of traditional building materials are natural products. They're wood, stone, clay derived, gypsum derived. These materials are hygroscopic. This is a fancy word, but it's one that's worth knowing. Hygroscopic materials are materials that absorb moisture from the air surrounding them. They tend to act like sponges, and almost all materials in a traditional or a historic house environment are hygroscopic. You could also, another word for that would be hydrophilic, meaning they like or take up water, they mix with water. Whereas most modern building materials are derived from petrochemicals, or they're, for instance, like fire, they're cementitious, fiber cement, a non-friable asbestos, fiber cement, very similar materials, cementitious materials. They have very low porosity. Glass, obviously, is vitrified. It's hydrophobic. We need to understand that's one of the most important dichotomies in conservation, in architectural conservation. It's the difference between hydrophobic and hydrophilic materials. And so modern materials tend not to absorb moisture so readily as traditional materials. What's the consequence? Well, we know that where water exists, so too often exists life. And living things like mold, termites, or those tend to prey on materials and consume them. Also, where water goes, impurities can go that can flow with water in solution, like salt. And when that solution dries up, the salt precipitates out into its crystalline state, and it can explode materials. That actually exerts a lot of force on a material and will make it basically fall apart. So salt attack, biogrowth, as we would call it, the fancy term, like mold, mildew, cyanobacteria. These are things that will slowly consume building materials. So we need to understand where water is moving, where water has the potential to fall out of the atmosphere, and how that interacts with building materials, okay? So, an important takeaway, even if you can't see it, materials in old buildings are often absorbing moisture. And once that moisture has been absorbed, it needs to have a way to get out, to dry, because the longer a material stays wet, the more likely it's going to host things that we don't want it hosting, like termites, for example, or mold or mildew, or salt in solution. So when we talk about old buildings needing to breathe, this is sort of what we're talking about. We need air circulation so that this water absorption can be given back out into the atmosphere. Finally, one last note on thermodynamics. I won't say that word again either. We'll just call it heat gain and heat loss. Thermal energy moves in three different ways. And you might remember this from junior high science: conduction, radiation, and convection. Okay, and all three of those are occurring in different parts of an old house. And that's inevitable. In fact, there's really nothing you can do to prevent that. You can only mitigate where heat gain and heat loss is occurring. And it's always my theory that you should be looking for the easiest or the lowest hanging fruit as ways to prevent unwanted heat gain and heat loss. So you might ask yourself, what part of an old building is the most active zone for heat gain and heat loss, where you have all three different methods of heat transfer occurring? And I'm going to give you a hint. It is not the windows. It's the roof. We'll talk a little bit more about roof treatments, but the roof is the part of the building that's more often than not always exposed to sunshine. It's at the top of the stack. We talk about stack effect. So it's all of the rising heat and humidity is building up right in your roof area. conduction, I mean, yeah, the roof bakes. If you go into an attic in the summer and feel the underside of the roof sheathing, that's putting a lot of, it gets quite hot, and then it radiates that heat down into the house. So the roof is really the number one place to think about when we're talking about mitigating heat gain and heat loss. So it's been a lot thus far. We've talked about appropriate expectations for old building performance. We talked about misconceptions. We talked about the wisdom of vernacular design and the physics that influence how old houses perform. Now we're going to get into green building practices and talk about, based on what we know now, talk about what does and doesn't work in an old house. Windows, the pink elephant. The window replacement marketing machine, as I call it, is formidable. I did just a little bit of research to see sort of how big is the industry for window replacement in the US. Well, I mean, how many billions of dollars are we talking about? And I found a consulting firm that is tracking this up at least until 2019, showing that in the replacement window market, there are over nearly 60 million units sold in 2019. And you'll see the majority, the healthy majority of them are made from composite materials and vinyl. We're not really sure what the others are made out of, probably aluminum, some wood. So this is a huge market, and you can imagine with that much money at stake, the marketing is intense and the messages that we are receiving as consumers are intense. There's a lot of pressure to replace windows as the number one easiest, best thing you can do to increase an old house's efficiency. And you don't want to maintain those old windows and paint them and deal with all that, right? Well, it can be a hard argument to make when that is sort of the cultural momentum is built up behind the marketing and replacement of replacement windows. But I would really espouse thinking about this a different way, and we call this life cycle analysis. The method used to evaluate the environmental impact, the holistic environmental impact of the product through its complete life cycle. And this encompasses the extraction and processing of the raw materials that make that product. You got an old house, it has wood windows in it. They exist. That wood's already been cut. Window's already been assembled. It's in place. The replacement window, vinyl, composite, these raw materials are being extracted and processed. Usually they originate as oil, the petrochemicals that create these materials. That new window has to be manufactured, distributed, trucked around, put on a train, put in an installer's van, trucked to your house, installed. And then we think about its use. What is its service life? How long will it last? How durable is it? If it breaks, how easy is it to repair? Or is it a proprietary type of construction with all these small extruded parts that can never be found or sourced or replaced again? And the last part is the disposal. It's the product's demise. How is it going to break down and decay? Will it ever break down and decay? In the case of many of these materials, no, they're non-biodegradable. So if we really think holistically about how we're operating within the environment and our net environmental impact as people on this earth, we really have to question how green, how carbon friendly is it to replace a viable window made from natural materials that we can repair with a new window that is going to fail in a much shorter timeline, can't be repaired generally, is based in petrochemicals and will never degrade. And I know too, how to repair old windows. It is an underserved part of our construction industry, not only in North Carolina, but around the country, people who specialize and can repair wooden windows. I am confident that we are already seeing in this state, more businesses step into that sector. It's a profitable sector, I believe. I think it will be increasingly well served over the coming 10, 20 years. And, for DIYers, it is not, I mean, it's not rocket science to work on Windows. And so and we can arm you with that information. You can always get in touch with us. But, you know, it's not just a aesthetic thing. It's a practical thing, keeping existing Windows. Now I'm being sort of cheeky when I say, can't we just use curtains? But to make old Windows feel a little bit more comfortable in the winter, but and in the summer. But this is something that we really truly believe in, just as practical people. So we can use curtains, you know, to be cheeky. We can also use storm windows, and storm windows have come a long way. So on the U.S. Department of Energy website right now, you will find these words, quote, replacing single pane windows with double pane windows that have high performance glass may be cost effective, but you could also consider installing exterior storm windows. Storm windows will produce similar savings at a far lower initial cost, which is true. But I would suggest folks acquaint themselves with all the new development that's happening in this sector. Storm windows have really come a long way. Interior storm windows are much more common now. They come with low E coatings on the glass, much more user-friendly attachment mechanisms. Here's one of the newer arrivals on the marketplace. It's called Indo. They're interior storm windows. And I say they're not your grandparents' storm windows anymore from the 1950s. It's super heavy plate glass, guillotine-like aluminum things that you're sort of afraid to touch, and they're always broken. You can't use them. You can't take them out. Storm windows have come a long way, and we're always happy to talk about options that might fit your house. Moving along, the other pink elephant, spray foam. Spray foam in a historic context. Okay, if we were meeting in person right now, I would poll the audience and say, based on what we've already discussed in this presentation, what do you think are the problems that could be posed by spray foam in a historic house? I can't poll the audience, but I guess I can just sort of go over them myself. Condensation potential. Okay, when you have, imagine this, so this house is siding on studs, obviously. There's no continuous sheathing because it was foamed from the inside and the foam is coming out between each board of siding. Condensation potential. This siding is going to be kept far more often close to dew point temperature. When it gets cooled off, it's going to have a harder time warming up. It will get more condensation on the exterior than it would were there an air pocket behind it as naturally designed as a vernacular building. Moisture entrapment. Spray foam insulation, there's two different types on the market. There's open cell and closed cell. Open cell spray foam is mildly porous. It does allow for some moisture transport, but not a lot. It's very, you know, it's not the same as an open air pocket with air circulation occurring between each stud. Okay. Closed cell spray foam, which is what we see here. This is foam in a can from it's marketed as great stuff. You might see it at Home Depot. It's called great stuff. It's used for sealing gaps, draft stopping, fire blocking. That stuff is always closed cell foam, and closed cell foam is essentially 100% water and water vapor impervious. So no movement at all. So trapping moisture up against a hygroscopic material like wood, a hydrophilic material like wood is a recipe for decay on a very short time span. And so I'm not optimistic about the survival of this siding, let alone the paint, for more than 8 years. Irreversibility. When you spray foam something, it's basically impossible to unfoam it. You'd be there for ages with a utility knife and a pick trying to pop it off. It's really an irreversible alteration. And so it really deserves careful consideration where it goes and how deep and how thick and why. And then life cycle analysis. You have to question, again, the use of a non-biodegradable petrochemical derived product for gain, for environmentally friendly reasons within a historic house context. Once stuff is foamed, it's not ever going to go back. Foam takes a very, very long time to degrade. And it's composed of resins that are highly refined chemicals. And so money where it counts. So let's talk about a better place perhaps to invest when trying to boost efficiency in an old house context. And I believe that that's in the realm of HVAC equipment and ductwork. You certainly want to invest before your units start to look like that, but possible areas for upgrades. Ductwork. Does your ductwork leak? Does it hemorrhage cool air when you're trying to cool your house? Making sure, is your ductwork insulated? Is it up in a blazing hot attic that has no insulation at the roof line? Could you, in theory, put some bad insulation in your attic to lower the temperature up there where your ducts are? Could you get new ducts that were air sealed so that you're not losing the air that your energy is cooling? Can you wrap it in R6 insulation to make sure that you're not losing that your ducts aren't heating your air conditioned air before it can be dumped into your living space? So ductwork is a really good place to look and to try to find areas for gains. Variable capacity equipment. What I'm talking about here are heat pumps that are able to run not just at full blast at 100%. Heat pumps that have different gears, like on a bike or in a car. They can run maybe at 75% capacity, at 50%, or even 25% capacity. The advantage to variable capacity equipment is that you don't experience what is called short cycling. Short cycling occurs when you have a large, overpowered, oversized air conditioning unit servicing a space where when you set the thermostat, for example, to let's say 72 degrees, you have such a robust, powerful system that it reaches 72 degrees very quickly and shuts off. When that happens, you don't get sufficient dehumidification in the space. And so you'll often have sort of a cool but clammy, uncomfortable environment, which you encounter in a lot of buildings in the South in the summer. And especially in an old house, like I said, with a porous building envelopes, you know that you have heat load coming in from the exterior. You have infiltrating humid air from the exterior. So dehumidification is really, really important. And the longer that you can dehumidify over a longer period of time, the more comfortable the house is going to feel at a higher temperature. So it's important to have, number one, a unit that's not too big for what you're trying to do. So if you're talking to an HVAC contractor, always make sure that contractor is actually doing a load calculation for your house and not just, using rule of thumb to spec a very large, powerful unit because your house is large, for example, or because you got tall ceilings or something like that. It's very much worth asking, have you done a load calculation? Is this equipment sizing informed by the actual dynamics of this house? Because you don't want a unit that's going to be too powerful, that's going to short cycle, and you're going to have a buildup of humidity in an overcooled space. Because then think again of the sweaty glass principle. You're going to have the possibility for condensation developing on your plaster, on your wood trim. I've seen this in historic houses in the Piedmont. So be intentional about equipment sizing. If you can spec variable capacity equipment that can run at a couple different power levels to lengthen dehumidification, that is a really, really great investment. You're going to see your energy bills go down, and I think you're going to have a more comfortable interior environment. And then if you're doing HVAC work, think about how the house is zoned. How many different heating and cooling zones do you have? Do those correspond with the natural situation of your house? Is it organized by floor? Is it organized by, the south facing part of the house versus the north facing part of the house, which is going to get less sun? Be deliberate about how the house is zoned, about where the thermometer, that's a typo. That's supposed to be thermostat placement. I literally been in a historic house in the Piedmont where the thermostat was in the attic. And, that's a problem because the attic is scorching hot. And so the system ran and ran and ran, overcooled the house. There's condensation forming on trim and mildew. So thermostat placement and programming. If you can get, new thermostats are really quite advanced in terms of how you can program them to run, not to run. So that's really a good place to look and invest to make your historic home more efficient and to lower your bills. And again, I was talking about variable speed equipment. They're able to dehumidify over a longer time span and at lower power. And then mini splits. You might have heard of these mini split systems. This is what they look like. They're composed of an exterior unit that interfaces. You hear the line sets coming in, the power supply. They interface with these different wall-mounted air handlers on the inside of a building. Now, and if you can get over the look of this in a space, and of course it's reversible, you hang it on the wall sort of like you would a picture frame. If you can adjust to the look of an air handler mounted on the wall, just think you don't need to install ductwork. You can have on-demand heating and cooling, very specific zones within the house. Don't need to build soffits to hide the ductwork. So we find that mini split systems are very efficient, very flexible, offer on-demand customizable heating and cooling for old houses. It's a good form of technology. So finally, to end the presentation, I've just got a few more, broader tips for sustainable old houses. Number one, this one might look familiar if you've done a tax credit project. Deteriorated historic features shall be retained rather than replaced. That's from standard number 6 from the Secretary of the Interior Standards for Rehab. And that is honestly my number one tip, to keep things out of the dump. Maintain your house and fix existing things on your house. Don't buy new things, replacement things that are made from petrochemicals that are not going to deteriorate, that are not going to degrade ever. Keep what you have, maintain what you have. That is a great way to be sustainable with an old house. Invest in HVAC equipment if possible. If not, maybe you can replace the thermostat with a programmable one and be more particular in how you heat and cool. If insulating, focus on the roof. Again, that's where you have all 3 different thermal energy transfer modes occurring at the greatest intensity. And be wary of spray foam in most all old house applications. I'm not going to say that there's never, almost all the time it's not a great idea in an old house. But if you're unsure, you want to talk more about it with your specific case, give us a call. Give your restoration specialist a call, and we can sort of review the dynamics and what's on the table and help you make a more informed decision. But most of the time, spray foam in an old house is going to result in some trouble. And this one might seem cheeky too, but number 4 is to be a little bit more old school. And by that, I mean, adjust your wardrobe and your bed linens to fit the season. Use your operable windows and place fans in the house. Use ceiling fans. Augment that passive ventilation that your house was designed to achieve. Spend time on your porch. Maybe if you don't have one, put a screened-in porch off the back or something. In the winter, if it's possible and safe, make use of a fireplace or a stove for point heating. Heating the places in the house where you're hanging out. Don't bother with parts on the second floor where you're not going to spend time. And then, of course, the modern equivalent would be the mini splits, which are on-demand heating and cooling appliances, similar to a fireplace or a stove in the winter. If you're using space heaters, make sure that your electrical situation is safe, and invest in that. We didn't even talk about LEDs and finding savings and how you light your house, but I would add that if I had a chance to edit this slide, I would say, make sure you've got LED fixtures. And finally, don't stress. Don't stress too much about your old house. If you can lower your carbon footprint in other aspects of your life, for example, by driving less or in a more fuel efficient car, eating less meat, buying less plastic, etc. So remember, our impact on the environment is holistic. It's not only through our house. If you've got an old house and you keep it up and you maintain it, that too is doing a service to the environment. It's keeping it out of the dump. So that is my spiel on sustainability in old houses. Again, that was the first time around with this topic, so I hope you got something from it. If you've got more questions or suggestions for other aspects of sustainability in old houses you'd like more information about, let me know and let my colleagues know. This graphic here shows you all 6 of us, all 6 restoration specialists, and how we divide the state. So I appreciate you tuning in and listening, and that's all I have. Thank you very much.
That was great, Brett. Lots of helpful information, and I really, really appreciate you sharing it with us.
Thanks, Christy.
This concludes our 3rd session of the 2021 CLG Virtual Training Series. We plan to release a 4th session soon, and once it's uploaded to our YouTube channel, we will notify you through the North Carolina Preservation Listserv. Remember, if you would like this session to count towards CLG training, please email me a brief summary. And please feel free to email us with any questions or comments. We truly welcome your feedback.